Okay, so we are on. I've got my pen. Good. All right. So we ended last time talking about the center of mass, and this chapter is going to cover like three main ideas. And so we'll have some definitions which we'll do checkpoints in, and we're going to see a lot of our examples probably tomorrow as we go through it. But we will see some, and we'll talk about them and discuss them. So, you know, as always, just chime in if something doesn't make sense. But you'll notice our slide count is quite a bit higher on this chapter than others. But there's a lot to do it. This is what I call the bridge chapter. So, and what I mean by that is in the rest of the course, we've sort of been adding piece by piece by piece by piece to our particle model. But now we're doing two things at once. We're adding new definitions and terms. We're expanding the complexity of what we can solve. So you'll remember, or you'll recall, as I said last time, we're looking at systems of particles now instead of just particles. So with a solid object, it's sort of, we sort of are expanding that by looking at the difference in trajectory of different parts of the object. But we're going to expand this to a system of particles, and we're going to see that there's some counterintuitive stuff going on there, and I'll show you what I mean by that. So let's sort of review here. If we look at this object center of mass, it goes through a nice parabolic arc. But if you look at the other parts of it as it's rotating, they have a more complex motion. All right? And the center of mass allows us to characterize one point of the system and look at the dynamics of that point of the system. Now, this is for one object. This is sort of looks a little bit like we've done before. What we're going to see is that indeed when we have two particles, I'm going to go back and forth between the last slide and this slide a bit, so don't worry. We derived finding the position for the center of mass last time, and we're going to do that again. But if you look here, you'll notice that when we look at a system of particles, the center of mass, abbreviated with COM, is going to be the point at which we analyze the system. But where is it counterintuitive? You might be saying, well, wait a minute, these are just 2-point particles. Where it's counterintuitive is that when we look at the system, we're going to look at the whole system at this point where none of the masses are. All right? That makes it a little strange because usually we have an object, we just shrink the object to the size of a point. Whereas here, now we have a whole system of objects and we need to pick the point where we can look at the entire system as if it were moving all at that one point. So it's a little bit, it's subtle, but it's there. And you can see right here in this system of two masses, you have the center of mass at a location in which none of the masses are. So that can be a little difficult. Okay, so I realize my mic volume. I've been trying to figure out the mic volume for a while, so I just don't want to be screaming at you guys all the time, which it might sound that way. Okay, so let's go back and look at our two equations for center of mass. Now you'll notice we looked at these last time, and again, this is one of those situations where I like to start with the second equation and see that this equation 1 here is just a special case. Now, what we want to look here and notice is that the center of mass is fundamentally, right? What is this? This is a position. Position. So in order to have a position, in order to find a position, you need to pick an origin. Origin. I'm almost sure I spelled origin wrong. That's okay. Oh no, I didn't. It's right there. Look at that. I feel like a spelling, awesome person. So we need to pick an origin. Now, instead of going through this, because again, we kind of went through these equations last time, and again, you can watch that video and see the details of how we developed it. We're going to go over, I want to start with the general expression of finding the center of mass, which we'll find in the third slide. But I want to point out some differences to you. So you'll notice that if we look here at these two setups, we can put our axes, we can put our origin. Hold on, I'm going to delete clear that and just pick a line. We can put our origin either here, or we could put our origin, say, here through the center of mass. All right, I tried to make this origin at the center of mass. I'll try and move it. It's not perfect, but you know, what are you going to do? So that origin goes, that axis point that goes at the center of mass. So you'll notice that in each of these situations, right here, if we put the origin at one particle, we can use equation 1, and we can write that you know, the what do we have here? Oh, hold on. It's equal to M1, M2, X2, right? Over M1 plus M2. So you'll notice when we do that, we'll get a distance relative to this origin. And when you solve that, you'll get, you know, this distance as your position. Whereas here, in our second picture, if you look here, you'll notice that the center of mass should be at 0, right? So you can get because you're going right through it, that will be the center of mass with respect to if the y-axis is in this axis. Now, what I want to point out here, and what you should be aware of, is that the position of the center of mass remains the same regardless of where the axis is. It's relatively the same between each picture, right? But the actual position will depend on the origin you pick. So you have to keep that in mind. Shifting your axis does not shift this actual position, but it might change the number at which that position is at. So think about that for a minute and see if that works out for you, to understand that difference. Make sense? Okay. I'm gonna assume it makes sense then and go on.
Could you give me like a real life, like the baseball? What does it mean? This coordinate system doesn't change.
So what that means is, let's look at a blank example. It might help. I'm going to go to the whiteboard, which I rarely do, but well, because it's weird. So essentially, you can make any system you want, right? So we're going to make an arbitrary system. It's hard to give it. You can put any object you want, whether it's flying or exploding. We'll see more of the examples as we go along and add a little bit more sophistication. But for right now, a system could just be, the simplest system to look at is just a static collection of particles. And we'll even do it in multiple dimensions, because I think this might make sense. So we'll call this M1, M2, so forth. We'll call this M6. Now, let's just, for the sake of argument, say that we don't know the masses, but let's say we can do all the calculations and do the center of mass calculation, which we still really need to extrapolate and get it, you know, become more comfortable with. But let's say we know we can do our stuff, and we know that the center of mass is at this point here. Okay. So now, what I mean by different axes is the center of I'm going to make several of them now. So let's look at, I'm going to make 3 coordinate systems. All right, 3 different coordinate systems. I'm going to put them at 3 different masses, and they'll be in 3 different colors. So each of these coordinate systems is pretty much independent of the others. All right? I hope you can't hear all the wind coming in through my, it's making me wish I'd done a better job with my Bluetooth in this computer, which I could have bought something a while ago, but I didn't. So anyway, if we look here, right? So what I mean by this is each color, each one of these colors here represents a different coordinate system. And this is just some different, whatchamacallit. These are just different arbitrary coordinates. They're all XY axes, all standard coordinate systems. So what I mean by different numbers is that it doesn't matter which, you could pick any coordinate system you want, right? The center of mass relative to all of the masses won't change, right? But in each coordinate system, the actual value will change. So for instance, to make something that looks semi-consistent, hold on here. All right, so for instance, here the center of mass is in the 2nd quadrant. So our center of mass green might be, you know, -10, 6. That's an example, right? And I'm just making stuff up here. I haven't calculated here or anything. We just want to understand the concept. If we look at the red coordinate system, right, the center of mass is in the 4th quadrant, right? So RCOM, no, bad. We're supposed to change colors. It's supposed to be dynamic and cool. That would just, that just sucks looking at it right there. So for the red coordinate system, it is not allowing me to change my color. So for the red coordinate system, right, RCOM might be, I don't know, it looks like it could be, you know, 10 minus 2, right? And I'm going to put equal signs here. I'm going to have a red equal sign. Hopefully it doesn't throw you off too much. And now for the purple one, we could have, we're in the 3rd quadrant, right? So RCOM might be -8, -7, right? And you can put the units on all these. So without having to switch colors for the things I left off, my whole point is that this position isn't changing, but the numbers that it's equal to will change depending on which of these axes you pick. And you'll only pick one axis, all right, or axis. You won't be adding lots and lots of them. So that's what I mean. So good. That makes sense? All right. Fantastic. Man, it is really windy up here. I'm almost afraid my air conditioner is going to just pop out of the window. Anyhow, I don't know if you can hear all that wind. All right, but getting back to our presentation. So if we're good on this, let's go to back to our files. Yeah. It's a windy day. So anyway, when we look here, that's what I mean about in looking at these two systems. Now, as we go forward, as we have an arbitrary system, if we look at something like the one we had, we can look at the center of mass for n particles. Say we have a system just like we looked at in the whiteboard, right? We can figure out the center of mass by adding up each of these m1, x1 terms, right? So first we have to pick an origin. That's what it's not saying here, right? So first you have to pick an origin. And after you do that, that will give you these x1, x2 values for each particle. Each particle will have a coordinate position on the x-axis. And all you have to do is add these collection of terms up and divide by the total mass. So another way to look at big M is big M equals just the sum of the, oh, now that's not making sense. Is equal to the sum of the little m's. Mi. Okay? So in that sense, we just can sum up all the m's, and that will give us our big M. And we can look at the x center of mass. You'll notice that on top, you'll have, I'll clear everything so you can see it more clearly. On the top, we have each of these terms being summed to, and we can look at the position for the x center of mass in terms of this very nice equation here. All right, so if we're looking at what we looked at for the whiteboard slide we just did, this works for the x component of the center of mass. Now, this can be generalized, right, to the other directions, and all you have to do is do the same thing in y and in x and in z, and you can get, using the same procedure, you can find the center of mass three-dimensionally. All right. So if you were able to pick an origin, you would be able to find the position, those numbers, using this formula of the center of mass of a system of n particles. All right. It might be tedious, but it's not hard. All right. So you're going to start to see that some operations, you've probably already seen this, but we should be getting to the point where we're differentiating between problems that take a long time but are actually quite simple. There's no thinking required. And then problems where there's not a lot to do in them, but it takes a long time to figure out what that thing is to do. Okay? So I think so now we can express this a little more concisely, and we can write down that the R center of mass, so remember, the only thing you want to see here that's different is that that I want to remind you, so that R equals X in the I hat direction, plus Y in the J hat direction, plus Z in the K hat direction, right? When you apply this, looking at the last slide, this becomes a trivial extension, right? A trivial generalization. What may not be trivial is that we have to, much like what we saw in the beginning of the class, where we saw that our delta quantities, our instantaneous quantities, as we took the limit, as the distance, the dt's became 0, began to look like a derivative. You're going to notice that with this sum, it's starting to look a little bit like a Riemannian sum. And as you take the limit, as these little mass chunks go to 0, all right, you're actually going to turn the sum into an integral. All right, and we're going to find that you'll have these coordinate integrals in mass. Now, if you do not have a uniform mass distribution, if you do not have constant density, these are very difficult problems. They generally require you to set up what's called a metric tensor. And each metric, so a metric tensor is, to find the metric of a system, is a 3x3 matrix, and each entry in the matrix is generally a difficult to solve triple integral. So you can think of each problem as, at the minimum, 9 gnarly Calc 3 problems. Which can be a bear. But in this class, thankfully, we're going to stick to constant density. And here, constant density is going to save our lives. Because remember, density is kind of trivially the mass over the volume. And it's constant, so we can look at both of those as constants. Now, where this is wonderful, where this really gets power for us at this level, is that it doesn't matter whether we're looking at macroscopic densities or parts or microscopic. And I have to be careful with my v's here because we don't want to confuse these with speed. So what this allows us to do, if we look at these integrals, we're going to see in the next slide, is we can use this very powerful relation. And let's take a look at one of the integrals. So let's start with we'll just start with x, but you can generalize it to the other ones. Let's start with x dm, right? So what we can solve for the density here, that rho dv is equal to, this is 1 over m. We can say that rho equals dm equals this, right? And we can also see that m is going to equal rho times v. Okay, so we have this is equal to our x com, right? But now when we plug this in the integral, hold on just wait 1 second. I've overloaded my symbols. I can already feel it. Yes, I'm already overloading my symbols. Or I'm not overloading them, but we're not going to make as many replacements as you think. We're only actually going to replace dm. All right, so we have 1 over m, our total mass, because that's a constant, right? And that's going to equal the integral of rho x rho dm. Or sorry, dv. And then this will be equal to then rho over m, right? Times the integral of x dv. And I don't want to write it this way, like where they've stopped. So you'll notice that we can look here at our rho over m, and we can simplify that to one thing, right? And you'll notice that if you solve for 1 over v, you get is equal to rho over m. So that's a constant, but I want to, so that's where we'll get our 1 over v from. But I want to point out to you that in this integral, it might be more easier to understand it this way. This volume is dx, dy, dz. If you have not taken calculus 3, you very likely have not seen an integral like this. But this is a triple integral where you're integrating over each dimension. All right? But I think it's more explicit this way than it might be, you know, with just a volume integral, because volume integrals it's kind of weird. But this makes a very difficult to understand mass integral into, at least, it may be a triple integral, but we're used to integrating position, Cartesian coordinate variables. Integrating the mass is kind of a weird thing. So having constant density makes this into a solvable problem. And of course, if we're only handling this one dimension at a time, it can be, these might be constants, and then integrating these will be trivial, right? You just get some area, and then you're only really integrating x, okay? So they're the easiest triple integrals to do in this case, but it's still a process, and it's one that I think you can understand the machinery without having to just accept that this is the way it is. So basically, when you can bypass one or more of these integrals if an object has symmetry, and you're gonna, if you go on in physics, you're going to see that setting up problems to exploit symmetry is a way to make really difficult problems into really easy problems, and that's a skill that we develop and use frequently. But there are times where symmetry just can't be exploited. Okay. So let's go on. We've got a good checkpoint, but symmetry can be exploited. So if the center of mass lies at a point of symmetry, symmetry can be exploited. If it lies on the line or plane of symmetry, if there is one, and then it need not be on the object. Consider a donut, right? So this is how to exploit symmetry, but let's take a look at that donut. So remember, a donut would look like this, right? I'm missing donuts. I guess I could go down to Dunkin' Donuts, but I miss my California donuts, to be honest. Okay, so you'll notice that this is solid, right? From the inner radius to the outer radius. But the center of mass is in the center where there is no actual mass. So you see what I mean? If you were to look at this donut system in the way we're talking about, you would look at it at just this point. But to make it perhaps make it sound a little more deep than it is, there is no donut at that point. So what I want you to do is now I want to consider this checkpoint, all right? And I'm hoping you all will be able to give me some answers here to see where we are among our understanding of this concept of center of mass, because it's really the calculation, as you can see, is quite simple. It's far more important to understand conceptually at this point than it is to like plug in a bunch of numbers. So the figure here shows this uniform square, right? You'll notice it says uniform square plate, so that tells us it's constant density, which has 4 identical squares at corners that can be removed. Okay? So we want to know the center of mass for each of these situations. You'll notice the center of mass of the square here, and then after the removal of certain plates, and each part will tell you where it is. So the answers can be very general. We don't need a specific point, right? So either quadrant 1, quadrant 2, quadrant 3, quadrant 4. You can be more specific, but you'd be along like a line, one of the diagonal lines, or on one of the axes, right? Like where would the center of mass go? So so I want to do parts A and B together. I'm going to do those. So let's take a look here at A, right? So if it's uniform and it's symmetric, where do you think you should? I'm hoping you can see that the center of mass should be right here at the origin. All right, for just the square. Got to remove that part. Okay. So so if you look at this symmetrically, everything looks the same going one way to the other, right? There's just as much on the x. If you look at the x-axis, there's just as much square above as below, and from left to right, there's just as much there too. So the center of mass will be at the origin. Now, if we remove square 1, so if we remove square 1, there's less mass. We'll block out square 1. So now if we block out square 1, we want to find first an axis of symmetry. And let me show you how to do that. So you want to look at where things look the same. So first of all, let's look at a few examples. No, not green. Let's look at a few examples, and you tell me if it's an axis of symmetry. All right. Is the red point, is these figures symmetric now about this red axis, this y-axis? I'm waiting for you to respond. No, it is not symmetric about the axis, right? Does everyone see that? I only got 2 no's, but you'll notice that to answer that question, basically look at both sides, and you want to ask yourself, does the left side or the left side look like the right side? You can see it doesn't, right? So that is not a symmetric axis. Now let's look at another axis of symmetry and see if that will. Let's look at another axis and see if it's an axis of symmetry. Okay, so there. Good. No. And again, you can see from the top to the bottom, it doesn't look the same. So we have to be a little creative, and I want you to see if you can guess the axis of symmetry, and then I'm going to draw it and see if what I draw is what you came up with. All right, so I want you to take a guess, a quick guess, and now I'm going to draw the correct axis of symmetry. Ah, some of you, yes. Well, one of you got it, one of you did not, right? It's going to be along y equals negative x, right? Because y equals x is going the other way, right? That's going, y equals x is going up this way. All right. So now if we look at this, we know, we can see that there's more mass in, let's go back to green. There's more mass over here towards the fourth quadrant, right? So what we're going to see is that our center of mass will move into the fourth quadrant somewhere along this y equals minus x line. So the axis of symmetry will give us this location of the center of mass, sort of, and we can see that because there's more mass in this fourth quadrant, we'll shift along that axis of symmetry towards there being more mass, right? So does everyone understand where the answer for A and B? Good. I want you to try C, D, E, and F on your own. And I'm going to give you about 2 minutes to do that, okay? Yes, Mina.
Just to make sure, C, when C squares 1 and 2, that means from the original one, right?
Right. So you can think of it as each time that it's reset, and then you this is a good time to do this. So you can think of each one as you hit the reset button and you start again, and it'll tell you which squares to move.
Okay,
so C right says remove squares 1 and 2. So now you got to cross this one out. Oh no, I don't have a pen. So that one, for instance, you'd cross this one out and 2 out, right? Yeah. There's an F there too. So let's take a look. All right. Oh, okay. Wait, F no center, no mass? No, F is with all 4 squares removed, not no mass. So F would look like this. Yeah, yeah. Well, not that big looping part, but you know, just the 4 squares removed. So let's take a look at each one of these so that we can get the yeah. Oh yeah, Mina.
Professor, I thought the little squares are like they were denoting the name of each quadrant.
Yeah, no. Yeah, no, they were just
Yeah, I
denoting
thought
the
they were
little.
separate squares.
Yeah, no, just these little guys here.
All right.
Yeah, Artin.
Yes, Professor. But you on F, we removed all the squares. No, there is no one. Each square presents a mass.
Right, but remember, only the squares are only these parts of it. Let me write it again. So the only thing we can remove are these little guys here. See? If you take out all 4 of those, you're still left with the gray area, so there's mass there. You can think of each of the green parts, you can put attach or unattach. Right? That's what's meant there. So, good. So let's talk about them pretty quickly. So I'll just I'll show you the axis of symmetry. That should make the answers make sense. So let me get my line drawing fun time tool out. So for part B, right, it wants to remove square 1 and square 2. So if we look at that, you'll notice that we get symmetry about the y-axis, right? Because if we take away both these, I'll just make x's on them to do shorthand, right? If both 1 and 2 are removed, everything's symmetric about the y-axis, and now we notice we have more mass. I'll go back to green. You'll notice you want to ask yourself, was there more mass on top or more mass on bottom? On the bottom. Well, there's more stuff on the bottom, so that will shift the center of mass to down here, right? So that'll be on the negative y-axis. This is just C. Just C. Somewhere in the negative part. Yes, yes. So that's going to be the correct answer for C. Let's clear and go to D. So for D, we're going to remove squares 1 and 3. So let's. So for D, we're gonna get rid of square 1 and square 3. All right. Now when we do that, we have to look at our axis of symmetry line. So we notice when we got rid of square 1, we'll use the same negative x line that goes through both. But you'll notice now we're symmetric completely about this axis. So anything we took off from square 1, we're balancing it with square 3, right? And in fact, it's helpful to make another symmetric axis in case you can't see it, to make 2 axes of symmetry. So let's make our first one again. All right, there's 1. Oh no, I messed that up. I'm having a hard time switching between the tools that I'm supposed to. My mind gets a little messed up there. All right, so we'll just do the best we can. I'm not gonna go too crazy with it. Let me see here. All right, that's gonna have to be good enough. But if we look here, the point I wanted to make. Oh, Artin, yeah. The point I wanted to make is, I'm just waiting for you to talk, Artin. Is that this other line of symmetry? You can see that if you remove 1 and 3, right? Let me get the pencil. Use red. If we remove 1 and 3, we can see that everything looks the same across both axes of symmetry, right? And that tells us that our center of mass will be at the origin. Still waiting for you, Arjun. You had a question? No?
I'm good. I'm good. This is from the first one that I had.
Oh, okay. Then I'll lower your hand.
Yeah,
All right.
sorry.
There we go. Okay. So that's where we get, so we'll see then there that for D, when we remove 1 and 3, we'll be at the origin. All right? Now, let's take a look here and remove 1, 2, and 3, I believe is part E, right? So we'll just take those out. And you'll notice we'll get here the correct axis of symmetry will go through like so, right? And so here you'll notice that you're symmetric about this axis and that you have far more mass in the third quadrant than the others. So that will move your center of mass somewhere into along that third quadrant, or in the y equals x line. All right, that's the y equals positive x line. And finally, if we remove all 4 of them, we've applied the removal symmetrically, right? And that means your axes of symmetries are the ones that are given, and your center of mass will again be in the origin. All right. So you can see the nice slide with all the answers. Notice that's just what we got. But I'm hoping that it makes some sense. You can, again, the more important goal than it's important to calculate center of masses for sure, but it's far, far more important to visualize how it's changing as symmetry changes. Because once you do that, the calculation is really quite trivial, right? You're just, the math level itself is easy. It's being able to picture how it's moving that will really guide you into setting up that calculation. And once you can set up that calculation, then you're almost 90% there. Okay? So I know it doesn't seem like we're like going gung-ho into it, but we really kind of are. And this is one of my favorite checkpoints because I think it's very complete and focuses on what's really important without bogging us down and doing a bunch of adding fractions, which is what we'd be doing otherwise. Now, you can also use symmetry to solve a difficult problem. This is sort of a classic physics problem, physics 1 problem, where, and I want to show you, it requires some cleverness, and it's either an example or an exercise. So I was actually assigned to do this problem when I was an undergrad. But I want you to look at each of the first, at this figure, and we're just going to concentrate right now on the first shape, okay? So concentrating on the first shape, it's sort of this weird shape that we can't really describe, right? It looks sort of like a weird Pac-Man with some anger issues here in the claws. I don't even know if you guys know what Pac-Man is anymore. But the question is, what is the center of mass of this shape? So when you look at it, it's not the first thing you might be tempted to do is say, okay, very confidently say, all right, well, we know that R is the, we can just look at it. We've got our origin. We're feeling pretty good. And we might want to say, it's just MR I over our total M. And we're like, okay, I can do that. But then we're like, oh, wait a minute. It's continuous. It's not points. So we can say RCOM right, is equal to 1 over M integral of R dm. And then you look at that and you go, I don't want to do that either. So, because setting up the bounds of that integral, you're going to find that with integration, the really hard part, more difficult sometimes than actually evaluating the integral, which can, as you all know from calculus, can be all sorts of fun, is actually finding the bounds and setting up the integral with the correct geometry so that it is solvable. That can be an issue. But what we can do is use symmetry. So when we look at these, and this one is not possible, right? So this is not possible because it's not discrete. This looks annoyingly hard. Looks too hard to do. So then the only toolbox we have left is symmetry. I'm going to give symmetry majesty because that's how we will solve the problem. All right, and this will sort of how shall I say, it will teach us something new through this example that we can do. So this object is hard to describe. However, we can describe it in terms of two circles, right? With the center of mass of one circle being here and the other being at the origin. So you notice you have these two circles. Now, sometimes, not often, well, actually more often than you'd think, but sometimes it really is easier to do two things instead of one thing. And we'll definitely take two easy things instead of two hard things. So the trick to solving something like this is to look at what's missing, right? And to saying, okay, let's find the center of mass of the small circle that's missing, and that'll give us one C of M. And I'm going to actually delete this stuff up here because I want to make a point about actually solving the problem. But just look at part B, right? So we can reduce this. Hold on, no, I want to make a straight line. Right, we can reduce this to two easy problems to solve. We can look at the center of mass of the small circle S, right? Oh, that's still dope. Still making a line. We can look at that. We can call that SCOM. And you'll notice we have the center of mass of the big circle C, COM, right? So if you look at this figure, we have the center of mass of the big figure. And now all you have to do, you'll notice D is sort of a throwaway figure, but the center of mass of the composite figure, all you have to do is now find the center of mass of the new system, right? So basically, let's sort of review this. You have this complicated object, right? You can break it up into two simpler objects to create a system of point particles. And then, so you have the center of mass of this circle, which is very easy to find. It just has a radius, right? It's at the center there, whatever distance this is. So this is a distance r. So you go there. You have this distance. And then you have this mass, which stays at your origin, the center of mass of the big circle, if it were complete. And then all you have to do is subtract one, one from the other, right? So you're taking away mass here that's going to push from symmetry. We already know that that's going to push the center of mass towards somewhere along the x-axis. Okay. I've just noticed Mina's question here. F, for the checkpoint, the center is at the origin. Yeah, for F, because it's a symmetric figure. You've removed all the squares. Yeah, Mina.
Sorry, the F was the response from the previous checkpoint, but I have a question. I know why it is for here right now. So yeah. I still don't get it because from C, center of mass for C is essentially the combination according to 1, 2, 3, fourth bullet point is a combination for the center of mass for both, right? That's
right. For A and B. So the way they're presenting it in the bullet point is the C here, right? You see what I'm pointing at?
Yeah.
So that is equal to A, this figure, plus this figure.
I understand, but it still doesn't, in my eyes, in my mind at least, it still doesn't answer the question of how comp P is found.
Well, P again, P is the center of mass of the plate, right? The whole idea is to find the center of mass of this plate in A. And so basically what you do is you look at the composite, you look at the part that's missing.
Yes.
Right? This circle is easier, so you can find the center of mass of this object, which is easy to find on this axis, and that goes down here to S. And then you do the same thing with the big circle. And you do that, you can add the plate back into this circle to find the center of mass of not the plate, but the plate plus the circle is also easy to do because it's a circle, right? So the idea is before, if you look at what I have up top here, and why I like writing it this way, is I've done those steps, right? First I found the center of mass for this small disk S, this auxiliary disk, and that's this point. Then I find the center of mass for the big complete, you know, S plus P or A plus B here, right? I find that center of mass. The next step is once you have these two center of masses, now you have an easy problem. Now you just have to find the center of mass. You sort of add these two together, or subtract them, as it were, and you can find the center of mass of the total of the plate by actually subtracting, right? Because if you had the center of mass here, and you were to add the center of mass of the whole plate, you're basically taking off a little bit of center of mass here by removing mass here, right? You're pushing the center of mass out this way towards X. So this allows you to do that. Okay, so all you have to do is sort of, I guess you'd really add the positions, because you need to get over here somehow. So you're just adding these positions together, and that will give you the center of mass of the plate, because the center of mass, symmetry allows you to do this. I'm wondering if the confusion is because we're arguing almost completely from symmetry, right? You can do all of these steps due to the symmetry of the problem. And it's not, and I think what the issue might be is it's not just, oh, well, here's the formula, do it, right? This is why I didn't focus on doing a bunch of examples with, well, we have this system, let's find the center of mass, let's do another system. And you'll find there aren't terribly many homework problems that ask you to do that either. What we're doing here is we're just looking and arguing from symmetry. So because of the symmetry about the x-axis, right, that tells us something. That tells us that the center of mass will be, we can sort of intuitively get an idea that the center of mass will be on the side of the x-axis from the origin, right? So we get that intuitively. Now, because of the missing part is a symmetric circle, we can find the center of mass of that disk, right? Say it did exist, and we can find the center of mass of the circle very easily if it were a complete disk. And then once we find those, and we can only do this step because of the symmetry. And basically what we're saying is that finding the disk S and disk P, right, the composite, are easier to find, and they help us set up an easy problem where we can just treat them as two systems, and then we can find the center of mass of this really system of systems, all right, which is represented by the plate. So I don't know if that makes it make more sense, but I hope you're seeing the reasoning behind how to approach it.
Abstractly, I do, but still, I don't know. Maybe I have an issue with the slide itself. It kind of like the fourth and the fifth point, bullet point, it's kind of confusing for me.
I actually haven't even read the fourth and the fifth bullet point, so let me look at them.
Okay.
So on the diagram, column C is the center of the mass for the plate, and S and disk combined. Okay, so the fourth bullet point is saying that is just talking about this point right here. So does that make sense?
It does. The thing is that when I have an issue, says the plate P and disk S, so the combination of it should be the center of mass.
Right, and that's what you get. P plus S equals this C, this big circle. So that's the composite. And all it's saying is that the center of mass of that composite will be the origin, right? Because it's a circular disk.
The reason I'm getting confused is I do understand it should be some. Well, not, I don't. I have issues with the fact that one disk and the plate, I mean, for plate P, the big one, right? Obviously, it's going to be the center of origins. I understand that. But if you combine and you add to it disk S, I don't understand how it should be there because we have some mass for the S disk too. So then that make it move. I just don't find y should be in the center of origins if you combine both.
Well, if you, again, so you're talking about combining both. The only thing you can combine are the plate P and the disk S, right? We're good on that?
Correct. Mm-hmm.
Okay. So the idea here is that everything is uniform and it has some mass. So when we put
That's
this
right.
here,
So if it's uniform, so for plate S, disk S, sorry, is uniform for the disk itself, and
right.
for plate P is uniform for plate P itself. But if you combine one on top of the other and you position disk S on top of plate P, how the center of mass is going to be still the origins?
Well, the mass will change because you're definitely adding mass, right? So the total mass, that's certainly going to change. But again,
True.
you can look at that as getting the total mass is not so bad either. Getting the total mass of this might suck, but if you were given the mass of this and the mass of the plate, you could just it would be pretty easy to figure out, right? Because although it's hard to figure out what this is, you can easily figure out the fraction of the circle missing from the plate. So if you had, for instance, if they just gave you a number, which I think when you saw this problem they do, if they said this section has a total mass of 5 kilograms, right? You'd say, okay, well, if the total thing is 5 kilograms, what fraction of the entire circle is this? That's easy to figure out, and you can add it back in. So getting a number shouldn't be a problem, right? So you're definitely adding mass when you pick this up into the whole thing. This is one mass, this is another mass, and then this mass is a composite mass, right? So I'm still not, so are you clear on that part? And I'm not sure that's what you're asking, but that's what I'm sort of hearing.
No, what I'm asking is if you're not melting one disk with the other to combine them so you have something uniform all out, you will end up having kind of like a more mass on the left side of the circle rather on the right side. So I feel like the center of mass shouldn't be on the origins, but more on the minus x.
That's where you're not. So you're making an assumption that I don't understand why. So imagine you had a very sharp laser and you had this disk, right? Let's start with C.
Mm-hmm.
So imagine you just have one thing. Now you understand why it's at the origin here. You've said that. So now imagine you have a very hot laser knife and you can cut out that circle. And the circle can just be placed in or out at will. It's removable. All right? So when you place the circle in here, there's no reason why there's no reason why it should be heavier when you have the whole thing.
Oh,
okay.
I think I see what I got. I thought the origin. Okay, so what I understood initially is that we have the circle on A, B, C.
Yeah.
Right, and then we subtract the mass, equal amount of mass, the original problem, right? From if we have from B, we subtracted from C to get A. That's why I understood for the original problem.
Yes, that's
right?
correct.
Okay, but on the diagram, on bullet point 4, it says it's combined.
Right. So that's well, you can look at it. You can look at it either way, Mina. You can add it or subtract it, right? So we can look at it as taking away part of C to get to A, or we can start with A in the same way, right? Because we now have two pieces. If we start with A and combine it with B, we get C. It works both ways. Going one way doesn't change the problem at all. It's reversible.
So my mistake was that and I'm sorry for this dragging you on.
These are the important things to work out. These are the very important things to work out.
My confusion was plate P. Plate P, yeah. I thought it was C, not A.
Oh, okay. Yeah. That'll get you going, and that's extremely important. It's extremely important to read the stuff carefully and multiple times, to work it out. Generally a good rule to follow is if you're confused about something, don't assume you've read it right. I mean, I read these. In fact, when I help students with problems, I very frequently say you need to show me the problem, because 9 times out of 10, when the student tells me the problem verbally, they've missed out, they're leaving something off that's clearly in the written problem. And I go, did you look at that part? And they go, oh, I didn't see that. And that almost always solves the problem. So it's a good thing to look at. It's a really good thing to have gone over, and it's a good thing to talk about. So don't worry at all. But with that being said, we are going to take our break, and so we'll take a break till about 2:20, and then we'll come back and we will move on from center of mass. Okay? And we're going to talk about Newton's second law for systems of particle. So I'll be back in a couple minutes, and then we'll start again, like I said, around 20 after. Sorry about that, everybody. I am back. Oh, are we talking about the Java? Yeah. Yeah. Good luck. Like I said, ask someone if they're willing to work with you. This is a good time to do that. You can use the chat room for that, no problem. And as a last resort, if you need to. All right. Let's get started here. We're running a little behind. Okay. So we want to talk about now that we've sort of introduced a system of particles, we want to apply the machinery we've developed previously to those systems of particles. So you notice we're coming back to Newton's second law. How do we apply Newton's second law for a system of particles? Now, the center of mass motion will be continued unaffected by forces internal to a system, right? So now we're adding this layer of complexity. So let's draw a short example and see what we mean by that. Now, in chapter 2, let's sort of review. In chapter 2, we had systems of one particle. We had objects, and forces would act on the object, right? We could have a tension or friction. You know, you could have some sort of force of push. The forces would act on the object. What we're really looking at here, though, what this first statement means is it's you have to look at the system of particles. Let me show you what I mean by that. So when we look at our system, I'll just make 3 particles. And let's say they have a center of mass. I'll pick blue. Let's say that this is the center of mass right there, right? The blue spot is the COM. Now, if we look at this first statement, it says the center of mass motion continues unaffected by forces internal to a system. So that means there could be forces between each of these objects, the forces in yellow, right? So each of these objects could have internal forces to the system and cause them to move, but as long as those forces remain completely internal, the motion of the center of mass remains unchanged. All right, so if this whole system is moving and internal forces are causing these to go apart, a good example of this is like fireworks, right? So in fireworks, internal forces cause it to explode, right? So you'll see these all explode and be pushed away from each other. But the center of mass motion remains unaffected, okay? So F net here for a system of particles is equal to the net force on the system will be equal to the total mass of the system, right? So m1 plus m2 plus m3 times the acceleration of the center of mass. So when it comes to external forces, we have to be careful between external and internal. They don't behave the same way. External forces affect the system as if they were all acting at the center of mass. All right, but internal forces can certainly change what the system might look like, but it doesn't change the motion of these internal, or of the motion of the center of mass. All right, so reminders, so we already did one. M is the total mass of the closed system. So we're talking about, you know, we're saying that nothing really enters in the system. And ACOM is this, so we already went over these reminders. All right, we don't need to do so again, you can read them. But hopefully that makes some sense. What's really important here is the differentiation between the effects of internal forces and how those change the center of mass, which they don't, and that external forces, when we're adding up the sum here, these are the sum of the external forces. All right, so we have to be able to tell those apart because conceptually it's very different. They have very different effects. All right, so we actually have the example of a firework. There's a few of them, but using the center of mass motion of equation. All right, and remember, there's not necessarily a particle at the center of mass, but just using that equation in a billiard collision, right, forces are only internal. So the force, external force equals 0, and A equals 0. Now, there might be internal forces in that collision, but the external forces are 0, all right? So a baseball bat, right? A equals G, so the center of mass follows the gravitational trajectory. The interesting one here is the one that we talked about before, an exploding firework, right? Or they call it an exploding rocket. So you'll notice that the center of mass, you start, right, and it moves just like you'd expect it to in projectile motion. And if you ever watch a firework display, next time instead of watching what's going on out here, watch the very center of the firework, and you'll notice that the whole thing moves as if it's still falling down. Now, it becomes too dim to see after a while, for sure, but you'll notice that it moves just like this. The whole thing sort of goes down. All right. Air resistance will, of course, change some of the dynamics here, but for the most part, you'll see it move just like that. So as long as air resistance can be ignored, it'll move like this perfectly. Of course, with air, that will lead to some interesting things, but you actually will see this for the most part, right? Especially right after it explodes for the first couple seconds. It'll move right, the whole firework will move in this trajectory, okay? Because again, all of those are internal forces. And again, the billiard collision only works with no friction, right? Friction would be a loss of energy. So we want to look at frictionless, no air resistance, no friction. Okay. So going forward, so now this is an interesting, extremely counterintuitive checkpoint. So two skaters on frictionless ice hold opposite ends of a pole of negligible mass. So an axis runs along it with the origin at the center of mass of the two-skater system. One skater, Fred, weighs twice as much as the other skater, Ethel. So what it's asking is, where do the skaters meet if A, Fred pulls hand over hand along the pole so as to draw himself to Ethel, and B, Ethel pulls hand over hand as to draw herself to Fred, and C, both skaters pull hand over hand. So the first thing what I want to do for you is I want to draw this picture, and then I want you to think about it. All right? So let's draw us a picture. So we have, we'll pick a better color. Let's go to red. So, well, the first thing we want to do is draw an axis, right? So Fred and Ethel are just pulling a rope. So it should be clear to you that they're on a frictionless surface and that we are talking about a one-dimensional line here, right? So we can call this our axis. I hope there's no confusion about that. We have I tried to be clever there, but I'm not going to do that. I'm just going to go back to the pencil. So let's see. So let's just pick a side for Fred. And let's pick a side for Ethel. All right. So we're going to go back to our red line. And dope. That is not great. So drawing the situation. No. I'm just gonna. There we go. And so what we're going to do is we're going to mark our origin is placed at the center of mass, right? So that's going to be COM. And as you know, if you remember, if this is Fred, Ethel has a mass of M. Fred has a mass of 2M. So the center of mass will be closer to Fred, right? So now that we can picture it, right? They're connected, they have a rope, and they're going to pull on each other. So where are they going to meet in each of these situations? I want you to give it just a minute or two of thought and see if you can come up with the correct answer to see where they're going to meet. Excuse me. Okie dokie. So what do you think? Good. All at the center of mass. Very, very good. Why? That is the important part. Yeah.
Okay, I'll give it a 10. In the first case, while Fred starts pulling himself towards Ethel, there's frictionless ice. So
Yep.
while he's moving towards her, she also moves towards him. It's unavoidable. Right. So this would meet at a midpoint, which I don't know how it could not be the center of mass at this point. I mean, and the same goes for B too, because it's the same concept, the same idea. They need to have a point of symmetry, which is a COM. Right. And the same goes for C2.
You're almost there. You have your explanation is good. You're just missing the right overall explanation, which is that all the forces are internal. So because all the forces are internal, everything you said follows exactly and correctly. So that's the thing, is there are no external forces acting on them. And as we saw previously, without an external force acting, the center of mass is in the same spot. So because all these forces are internal, they have to meet at the center of mass each time. Artin.
Yes. So Fred moves and Ethel is not moving on the A question, correct?
No, Fred says Fred is pulling. It doesn't say Ethel's not moving.
Yeah, okay. So as the pulling does, okay, so if the one moves and the other moves, is not right. If the one moves and the other is not moving, then the center of mass is moving also.
Nope.
If one is moving and the other not.
Nope, that is not correct. There's internal the way that this looks, the way this is set up. In order to move the center of mass, you'd have to move. You'd have to have external forces acting on the system. If you have no friction and only internal forces acting, I'm not saying it's intuitive. I'm not saying it's intuitive at all. It's again counterintuitive, but you will because of the forces are acting on each other, They may move at different speeds, things like that, but the center of mass will remain unchanged. And it's actually fun. You can actually show this experimentally to be true.
Okay.
Okay. So remember, you don't have one. If you now in what you're talking about, if one is moving and the other is not moving, then yeah, you're changing the center of mass, but you have some force holding the other one back. But if it's frictionless, they both move. You know, as one pulls, the other one starts moving. It does not say one stationary and the other one moves. That's important to know. Okay? All right, so let's move forward. And now we finally get to sort of, we get to the meat and potatoes of the, well, we're at basically part 2 of the chapter, right? So that was basically our center of mass argumentation of the chapter. And now we'll sort of wrap up by trying to get through momentum today. Momentum is sort of the shortest part. And then I'd like to spend almost all of tomorrow talking about collisions and impulse. I think we might get to impulse today, but I'm not sure. So linear momentum, all right, we're introducing a new quantity. Linear momentum is equal to m times v. And you'll notice that momentum is described with a p, and it's a vector quantity. Now, one thing to notice about momentum, it does not have its own units. The units of momentum are kilograms, meters per second, and that's it, okay? So the momentum, you'll notice, points the same direction as the velocity. It's scaled by mass, and it can only be changed by a net external force. And in fact, when Isaac Newton first thought of, let's take a look here, when he didn't really think of force as F equals ma. That's not how Newton thought of it. And if you'll notice, right, we can see that this is equal to m times dv dt. And the m is just a constant, so we can put that in here as d dt. I don't know why I put those parentheses in there. I was thinking about those parentheses. And remember, mv is just equal to p, so the force will be equal to dp dt. And in fact, if you read Newton's works, he will often write F equals p dot, which was Newton's notation for a derivative. A time derivative was a dot. So that's how Newton thought of his second law. So that is critically important. But one of the things about momentum is it gives us an idea of scale and inertia in a way that just speed doesn't, right? So if you ask yourself, what would you rather get hit by, an object moving at 10 miles an hour or an object moving at 100 miles per hour, it could seem to pick the object moving at 100 miles per hour. But if I told you the object moving at 100 miles per hour is a baseball and the object moving at 10 miles per hour is a train, you're all going with the baseball, right? Yes, you might get a bruise and break a bone, but you are going to survive that collision. You are not going to survive the train, right? And we can see that the mass gives us an idea of which one we would less want to be hit by, makes it a little more dynamic, but it relates it very directly to force, right? If you get hit or you're struck by something, there's a change in momentum, or that change in momentum exerts a force on you or on a body, okay? So, yeah. So that's sort of the basics of momentum. And as we're going to see, there's a lot of applications to momentum. We'll be talking about them for a while. But the main thing we want to see is that it's related to, it's the product of the mass and the velocity. It's a vector quantity itself. Does not have special units. And it gives us how Newton thought of force. All right, F is equal to dp dt. All right. So now we have a nice little checkpoint here. If we're looking for a system of particles, we can say that the momentum, big P of the system, is equal to m, the total mass of the system, times v at the center of mass. But this should be as difficult and unintuitive as the last checkpoint was. This I like to do because it gives us right back to an easier checkpoint, okay? So the figure gives the magnitude P of linear momentum. So you'll notice you have P on this axis, and versus a particle's t-axis for the moving particle along an axis. So a force directed along the axis acts on the particle. So it wants us to rank the 4 regions indicated according to the the magnitude of the force greatest first, and in which region is the particle slowing. So if we look here, the thing to recall is that force is equal to dp dt. So given that, it should be pretty easy how to answer this question. So come on, what do y'all think? I got lost in thought there for a minute. Good, I knew you all had answers. So now, if we look at it, it's definitely 2 equals 4. So if you look here, it's a little hard to tell, but let's see if we can extend the lines and see. Let me see here. Let's do red lines. All right. So I'm going to try and do a red line of the same slope. So that's parallel there. And now we can look at another line here. When I make the lines bigger, I think it's a little easier to see that the slope of 1 is going to be greater than the slope of 3. All right? So we definitely have 1 is going to have the biggest slope, because remember, dp dt is just the derivative, so it's the slope of the tangent line, right? And then 3, but you'll notice that 2 equals 4, which some of you got, but it's not greater or less than, because remember, we asked for the force, which is the change in momentum, not the momentum itself, right? So does everyone understand that part? Because we got some different answers. All right, good. Now, part B asks, in which region is the particle slowing? Not is it moving the slowest or has it stopped, but in which region is it slowing? So you'll notice as we go through, the momentum is increasing, right? It's increasing. And then the momentum is just not changing here. Here it's decreasing in 3, so it's definitely 3, right? Because we can see the momentum is decreasing. And then 4, it's not changing. So the only region in which the momentum is changing is region 3. Okay? Everyone is good on that one? Okay. So, all right. Good. So now what we want to see is that the linear momentum of a system of particles, we're moving back to this, we want to reemphasize that we're talking about systems here, so things like center of mass apply and all that. The linear momentum of a system of particles is equal to the product of the total mass of the system and the velocity of the center of mass. We saw that, but let's write that equation again so we can see it in sort of all of its glory. So P system is equal to the product of the total mass, m tot, times v of the center of mass. And these are vectors. Okay? So that, you'll notice I have some prefixes here, or suffixes rather. So the one under P here is sys, S-Y-S. M is tot, T-O-T, total mass. And then COM for center of mass under the velocity. All right? And of course, we can take the derivative in the same way and get the net force on the system of particles. Now, with the language we're talking about, you'll remember we talked about systems, and we introduced the idea when we started talking about energy, right? And we did that so that we could develop conservation laws about energy being transferred within a system. And we're actually going to find that we can use the same setup or same structure of systems to talk about momentum changes within a system, and we're going to see that linear momentum is actually conserved in a system. That's what we're building up to in the chapter. All right. So, so we can see here that without a net external force, right? Because only a net external force can change the linear momentum, but without it, the total linear momentum of a system of particles cannot change, and that means that if it's a closed system and only internal forces are acting, momentum is conserved. Okay? So pretty cool. All right, so now we're going to wrap up today starting with collisions and impulse. So we're going to talk about impulse, and we'll get to collisions. We'll expand our ideas of collisions tomorrow. Even if we end here with a little bit of with time left, it's a good place to end. I don't want to get too far into it because again, I'll want to review impulse tomorrow so that we can sort of get a better grasp of it. But we do want to introduce impulse, and it's a little good. So the next test covers lectures up through today. Collision and impulse will be on the final, and linear momentum and center of mass will be on test 2. So we are now done with test 2 stuff, which is why May 19th is a fair time to ask that question. So I believe I have to post some more homeworks on it, and I'll do that ASAP. But the next test is, we announced that, but that's okay. The next test is going to be, so we have your guys' lab on Tuesdays, so that will be on Tuesday, May 19th will be your next exam. Okay, so test 2 is chapters 5, 6, 7, 8, and up to 9.3. Okay? Yeah. Nice trying to get out of chapter 5, but yeah, no. Chapters 5, 6, 7, 8, 9 to 9.1 to 9.3. All right. So, okay. May 19th. So we're going to do it the same way. I thought the setup worked. Everyone seemed to get it in. It seemed to be okay. So what, for the exam or for today? I take attendance at the end. I'll take a picture of my phone. I need to update all that at some point officially. But I've been taking pictures of the attendance as we do it. So let's get on and start. We're not leaving yet though, so don't get ready to go. We still have 20 minutes, and I want to introduce impulse, at least today. I do want to go over impulse again tomorrow though. So we've got some checkpoints and some stuff to work on. So we want to introduce this quantity here because in a way it can look very difficult, but it actually can make hard problems a little bit easier. So when something collides, right? So if we have some sort of collision, right, against a wall, the impulse is the hard part, is what goes on right here during this collision, all right? And the impulse is defined, you'll notice it sort of looks like the definition of work, but we're integrating with respect to t, okay, not position. So when we look at this integral, the impulse is the force under some small amount of time, and we can integrate that. So that means what that means is we're really going to look at the area under the curve. So this means that the applied impulse is equal to a change of momentum in the object during the collision, right? So let's take a look at where we get this. So we're defining J. I'm going to clear this object here. We're defining J, right, as equal to delta P. But if we start with Newton's second law, we can see that dP will equal F dt, and this implies that delta P, right, will be equal to the integral of F dt. All right, when you integrate P, you'll integrate it from P final and P initial. That will very naturally give you delta P. Okay, just like when we integrated in kinematics and stuff, we would actually get delta X's and delta V's and stuff like that. Okay, so hopefully you can see where the structure of where these equations come from. But like I said before, and I want to draw it again, what we're describing here, impulses, these change momentums, if you're going along and you collide with a wall, this part here would be the impulse, and that's what we want to talk about. Okay, so now the equation can be written component by component like other vector equations, and we're going to find that that is incredibly important. So here, the impulse of the collision, because it's an integral, right, if we have f of t, is equal to the area under the curve. Now, again, as we all know with integrals, there's no fundamental theorem, well, there's the fundamental theorem of calculus, there's no chain rules for integrals, right? So this is what makes integration fundamentally a more headache than a derivative. But since we're integrating, we only actually need to know the area under the curve. So if we can somehow get an average force and make this area an equivalent area that's easier to compute, right? If we can somehow take an average or get an average force, then instead of computing a difficult integral, like so, f of t, we just have to figure out, if we have this average value, we just have to figure out what this area is, and that gives us our average force. So even though complicated stuff is happening in the collision, if we can somehow intuit or get f average, right, then J will be equal to simply f average, a constant, times delta t, and that will be equivalent to integrating this function. Okay? So this is a fun one because impulse sort of helps us understand how to survive things like plane falls and gives us some intuition about falling down from large distances. So I like this one. So a paratrooper's chute fails to open, lands in snow. and he is hurt slightly. Had he landed on bare ground, the stopping time would have been 10 times shorter and the collision lethal. All right? So does the presence of the snow increase, decrease, or leave unchanged? A, the paratrooper's change momentum. B, the impulse stopping the paratrooper. Or C, the force stopping the paratrooper. So take a look at this equation, right? And remember also that J equals delta P. And ask yourself what's changing. And keep in mind that we have T snow equals 10 T ground. Okay. So think about what's changing and what's not changing. All right, so if you're struggling with it or not knowing what to do, let's draw some pictures. So I'm going to delete what's going on pre-checkpoint. Now, think about it this way. Let's look at the moment. So here's the ground. All right, and here's our parachuter the moment his parachute doesn't open. So in all of these, when we're looking at this in every situation, well, let's take a look. You start with the same V, right? V equals V naught. Now, after the collision, what's the velocity equal to, one way or the other, whether you land on snow or on the ground? The snow you're slowing down. Remember, impulse tells us about 2 times, and the impulse is what happens in between before the collision and after the collision. All right, so the impulse, so that's in a way the impulse that the snow will flatten the curve, essentially. Yes, that's actually exactly right. But when we look at it here, will that impulse change? Think about flattening the curve. Does flattening the curve decrease the number of people who will get the disease? You have to think of it that way. It's the same question here as does flattening the curve change the overall impulse? Now again, we can look at that by understanding what's the final. So at T, at this point in the curve, before we have the collision, we'll have some, we'll have some V naught. And again, V naught here isn't really helpful. We'll call this V naught 1. When we fall, will the fall semester be online too? That is a great question. I do not have the answer to it. I just asked the president of the college that today. I had a meeting with him, with the president and the provost, and I'm telling you horse to mouth. The answer is it's actually a CUNY decision, which probably comes down from state guidelines. So, but they do need to know soon because, like I've said before, scheduling is complicated. So I need to know exactly what I'm scheduling, and I don't know what I'm scheduling. I mean, I have the CUNY first schedules, but like they're talking about doubling up the lab. I mean, they're talking about all sorts of weird stuff. So yeah, no, unfortunately, we don't have that yet. But this V naught is not helpful, right? We start off with some V naught when we realize the parachute, but if you look as we go down, we're not colliding yet, right? So we want to look we want to cross this out as being unhelpful at the moment. And we want to look at the V right before the collision happens. So we want to look at V here. We'll call this V naught. But then what's the velocity after the collision? In either case, what's your velocity after the collision is done and finished? After you fall? 0. Good. So does it matter whether you have, so let me ask, before you hit the snow or the ground, does it matter whether you have snow or ground, whether you have V naught? Will that change in any of the situations? So the question is, will V naught change in any of these situations right before the collision? So will V naught at this point of the collision change whether you have snow or no snow? No, of course not, right? You haven't even interacted with it yet. So if you look here, the first thing they ask is the paratrooper's change in momentum. So the momentum, delta P, is equal to m v final minus m v initial. And as we can see from this whole thing, that doesn't change, right? Whether we have snow or ground. So, so what we can see is that the momentum remains delta P, doesn't change, right? Delta P does, ooh, harsh. Misspelt does. That's as good as I was feeling earlier in the day about my spelling. That's hurtful. Does not change. Now, B, right, is does the impulse change? J equals delta P. So J doesn't change either. And you'll recall, as with flattening the curve, it actually won't decrease the number of people who get sick. It will decrease the number of people who are sick at any given time. And basically what's at risk, we flatten the curve, or the goal of flattening the curve is to not overwhelm the health system, not to prevent people from getting the coronavirus. People are going to get the coronavirus. It's going to happen. And the area under the curve doesn't change. Just like here, the impulse doesn't change, right? You have the same change in momentum. But if you look here, the momentum, it asks about the force. But you'll notice that the momentum, or the change in momentum in the impulse, is equal to 2 things, right? And in the snow, if the time goes up, the average force goes down. So the average force will be 10 times less and actually decrease with the snow than it will if you just hit the ground, because it all depends on your collision time. So actually, if you are falling, your number one issue, if you wish to survive your fall, or you see something coming, or you're in a car crash, is to elongate your collision time. All right, that's the best thing you can do to survive. So if you're on a plane, for instance, right, and you're not going to survive the plane crash, but if you want to increase your odds, you could put on your life preserver right away and inflate it and get the cushions, take out the seat cushions and wrap them around your body. Every microsecond of increase of collision time will drastically increase the likelihood you survive. And if you do that, you might have an extremely small chance of surviving, right? But again, if your plane is crashing and you can leave said plane, you also can't jump too soon, because if you jump too soon, you'll die of hypothermia long before you hit the ground. So like if the plane starts falling and you all of a sudden decide, oh, hey, we can blow off the thing and get the unpressurized, first you'll suffocate. Well, first you'll run out of air. So the first thing is if you jump out of a 747 cruising altitude, the first thing you have to do is have enough air to survive. The second thing you have to do is have it be warm enough to survive. Once you have those 2 things, then if you're like 10,000 feet or so where you can breathe and it's not too cold, then you can jump out of the plane and try and survive. And if you can elongate your collision time, then you will make it. So as you can see, there's a lot working against you in a particular plane crash. To end on a very happy note for today. Just donate. Yeah, hard to swim with broken bones. This is true. It's the surface tension of the water will make it indistinguishable from landing on concrete. So the goal is to land on either trees are your best bet, actually, and then snow. But trees are usually all year round, and snow is seasonal. So if you can land on, so trees are your best bet, and snow is your second best bet. And then if someone can, if you happen to find someone with a giant inflatable air pad, that's your third best bet. Okay, so I think that is going to end up being a good place to stop for today. And we'll pick this up tomorrow. And Brandon wanted to talk to me after class about lab. So let me, I just got to take a picture. And so let me get the camera, take a picture of the list. I may as well update these this weekend or try and get that because the school needs to know who's doing it. Okay, I'll see y'all tomorrow. Thank you very much. Oh, I gotta stop recording.